Let's talk about solving some of the harder trig equations that you might see coming up in your calculus courses. And we'll work through a couple of examples and we'll talk about our reasons why we're working them the way that we are. Let's start with sine of 2x equals 2 sine squared of x. Notice here that the problem is that the arguments are different. Here I have a 2x, here I have an x. So I need to convert one into the other. So I think about my trig identities, and one trig identity that I remember is sine of 2x is equal to 2 sine of x cosine of x. So we're going to use that here to rewrite the sine of 2x. So we'll write that as 2 sine of x cosine of x equals 2 sine squared of x. Now, since I have a 2 on both sides of the equation, I can just go ahead and divide that off. But notice that I don't want to divide off a sine of x, even though I have one of those on both sides of the equation, because it has a variable in it. And we never divide by a variable. If we do, we're going to lose a possible set of solutions. Instead, what we're going to do is we're going to move it all to one side of the equation and factor. So I'll subtract the sine squared of x from both sides. So we get sine of x cosine of x minus sine squared of x equals 0. Now they have a sine of x in common. I can factor that out. Sine of x times, that leaves a cosine of x minus a sine of x. So once I have it factored, I set each factor equal to 0. So I'm looking for where sine of x is equal to 0, or where cosine of x minus sine of x is equal to 0. Now, sine of x equals 0, if I remember my unit circle, that happens when x is negative pi, 0, pi, 2 pi, and so on. So I'll put a little dot, dot, dot at the beginning and a dot, dot, dot at the end. That ellipsis indicates that the pattern continues in that fashion. But that's not the most compact way to write it. What we're trying to write is it happens every pi. So a better way to write that would be to write that as k times pi, where k is any integer. And that plugs in the negative 1, the 0, the 1, the 2 that are the coefficients of the pi's right above them. All right, now let's solve cosine of x minus sine of x equals 0. Those solutions come from the unit circle, so we can look for where sine and cosine are equal. Or equivalently, if I want to add that sine to the other side, I could also think of this as where tangent, which is sine over cosine, is equal to a 1. So I'm looking on the unit circle either for where sine is equal to cosine or where tangent is equal to 1. That happens at pi over 4 values that appear in the first and third quadrant, but not the second or fourth quadrant. So that would be at negative 3 pi over 4, positive pi over 4, 5 pi over 4, and so on. Now notice that what we did is we identified one value, the positive pi over 4 that happens in the first quadrant, and if I subtract pi from that, I get to negative 3 pi over 4. If I add pi to that, I get to 5 pi over 4. So what I'm really doing is I'm taking pi over 4 and I'm saying plus a multiple of pi. So again, I'll write that as pi over 4 plus k pi, where k is any integer. All right, I think we have time to do just one more. We'll try and make it a little fast. Let's look at cosine squared of x equal to 3 plus 4 times the sine of x. Now here the problem is that I have a cosine and a sine. So I need to get those to be the same. So how do I convert a cosine into a sine? Well, there are a couple of ways I can do it. I can look at my identities and try and relate them. One identity that I see is sine squared of x plus cosine squared of x is equal to 1, my Pythagorean identity. So since I have that memorized, I can use that. I can solve for cosine squared. I can say cosine squared of x is equal to 1 minus sine squared of x. Now we can substitute that into our equation over here. 1 minus sine squared of x equals 3 plus 4 times the sine of x. Now I can get everything on one side of the equation. I'll add the sine squared to the other side, sine squared of x, plus 4 sine of x. Now we're subtracting the 1 to the other side, combine it with the 3, and we'll have a plus 2. Now notice that what I have here is I have sine squared of x plus 4 sine of x plus 2. That's kind of like a quadratic. That's kind of like a squared plus 4a plus 2, where I'm letting a be the sine of x. So I can handle it just as I would a quadratic. I can try and factor, or I can try and use the quadratic formula. So in this case, I'll use the quadratic formula. My a is a 1, my b is a 4, and my c is a 2. And if we don't remember, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. So now if we apply that here, now remember, this is supposed to be equal to whatever my variable is, but my variable in this case is sine of x. So we're going to go sine of x is equal to negative b is 4 plus or minus the square root of b squared minus 4 times a times c, all divided by twice a. So simplifying that, we get sine of x is equal to negative 4 plus or minus the square root of 16 minus 8 over 2. That would be negative 4 plus or minus the square root of 8 over 2. From that square root of 8, I can break that down into 2 cubed. So I can bring out a 2 and leave 1 inside the radical. Everything divides by 2, and we get negative 2 plus or minus root 2 when I simplify it. So that gives me two solutions. Sine of x equals negative 2 plus root 2, and sine of x equals negative 2 minus root 2. Now immediately I can say this one is not going to work. Why is that not going to work? Remember, the range of the sign goes between negative 1 and positive 1. But negative 2 minus root 2 is going to be outside of those values. That's definitely less than negative 1. So we're not going to get a solution from that. But we are going to get a solution over here. Negative 2 plus root 2 is going to be a small negative number. So to solve for x, we would say x is equal to, well, I've got to use my inverse sign here. So it's going to be the inverse sign of negative 2 plus root 2. But remember, that's only a single solution. It's a solution that's in quadrant 4 or quadrant 1 are the only quadrants where the inverse sign is valid. So since this is a slightly negative number, that's going to be a quadrant 4 angle. So I also want to pick up the angle that's in quadrant 2 that would be equivalent. So my second angle would be this guy plus pi. Now remember, this one's the quadrant 4 angle. This would now be the quadrant 2 angle because we added pi to it. Now if I add pi again, it would take me back to the quadrant 4 angle, and then if I add pi again, back to the quadrant 2 angle, and so on. So in general, I would say my solution is the inverse sign of negative 2 plus root 2 plus k times pi, where k is any integer.